Analyzing certain properties of functions. So we talked about domain. Now let's talk about this whole idea. It's just a word that we call average rate of change. Okay, this is just a fancy word for something very simple when it comes to a function. But then from there we're gonna get the idea of this expression, difference quotient, and this is going to play a central role. If any of you have to study calculus, this is a very important idea. Okay, this is the birth of the notion of derivative. So you have to be able to compute difference quotient. So let's talk about that now. It also has some applications in physics, like for example, if the function that you are analyzing happens to be the position function of a particle moving over time, then to ask about the average rate of change of that function is equivalent to ask for the average velocity of the particle over that period of time. Okay? And then similarly, if it was a velocity function, then the rate of change would be the acceleration of the particle, and so on. Okay, so this idea, it has a lot of applications in physics and so on. But we're just going to look at it from the mathematical point of view, and it's actually pretty simple. You just need to know what it is once you see this word. Okay, so let me give you an example, and then we illustrate what that is. So consider the function f of x equals x squared over 2 plus 1. So this is a function, right? By the way, what's the domain of this function? All real numbers. Good. So here you can plug in whatever you want. So let's consider this function, and then the question is find the slope of a line that passes through the points 0, f of 0 and 2, f of 2. So remember, to define a line, you need to provide 2 points. Okay, because 1 point is not enough. So here is a function, and then let's find the slope of a line that passes through these 2 points. So these, of course, these are points that lie on the graph of the function, right? Because I'm telling you that the y value is obtained by plugging in the given x into the function. So here there's not really, there's no need to sketch a picture for this, but I will do it just to, have some practice, because we haven't done anything like that yet, but I know that most likely you already know how to sketch functions in general. So we're going to study in a certain section, actually in the next chapter, how to deal with functions like this, so we don't have to do what we're about to do, okay? But anytime that you encounter a function and it's a formula that you have no idea how it looks, what you can do always is do a table of values, okay? Just start plotting some points, then you put them on your x, y, and then you hope that you kind of get a pattern, or you see a shape that then you can trace out and get an idea how the function looks. The problem with this is that it doesn't tell you the whole story. Maybe when x is between -1000 and, I don't know, and -500, you're probably not plugging in those points anyways, but then you're missing the shape of the function. Maybe the function behaves differently in that interval, okay? So table of values is not a good idea. It's only good if you can plot thousands of points. That's what computers do, okay? But we don't do it. So we just want to plug in a couple of points and then be able to tell what's going on. So that's why we're going to spend time later on giving a function, a particular type of function, how we graph it, okay? But right now, since we haven't talked about that, then let's just rely on table of values and, take it on faith that the shape that we see is what's going to be happening, and then later we're going to be able to understand that better. Okay, anyways, so I'm going to sketch a picture. So I'm going to do a table of x and y. So here we're going to choose an input, and then the y value is going to be given by our function. So our y here is just f of x, okay? All right, so something else also is that you are the one responsible for picking the points, okay? So because the domain here is all real numbers, then you should have a sample of both positive and negative inputs, okay? Because if you only start picking positive stuff, then you miss what happens on the negative side. So you need to pick both sides. And then, technically you can pick whatever you want, but also, do yourself a favor and be a little bit smart in the sense that here there's a little fraction. So you don't want to pick numbers that then will give you decimals and fractions and so on, because when you plot that point, it's going to be a mess, okay? So for example, because here I have a fraction, and it's divided by 2, I'm going to pick values of x that we guarantee that x squared is an even number. Okay? That way we can nicely divide by 2 and going to have nice integers. So for example, I'm going to pick 0. I will skip over 1 because if I pick 1, then I'm going to get a 1/2. I don't want to deal with that. And then I'm going to pick a 2. Okay? And that probably will be more than enough. Otherwise, things are going to get too big. So I'm going to pick a 0. I'm going to pick 2. Then I'm going to pick -2 just to get a feeling of what happens on the negative side. Okay, maybe let's go to 4. Then I'm going to pick 4 and then -4. And then definitely I will stop. So again, I'm skipping 1 and 3 because then I'm going to be having some fractions in here. Okay, I don't want to deal with that. Anyways, we find the y's now. So this is just plugging in. So when we plug in 0, we get 1. When we plug in 2, what do we get? 4 over 2, that's 2 plus 1, that's a 3. When we plug in -2, what do we get? If we plug in -2, we get 3. Good. If we plug in 4, what do we get? 16 over 2, that's 8, plus 1, that's 9. If we plug in -4, what do we get? 9. Do you notice something interesting in here? What do you notice? Okay, is there any other pattern that you see? This will hint at the next section. Yes?
That it's gonna be like symmetrical.
Why?
Because it's gonna have like the same y value like the inverse of the x.
Okay. Don't say it so complicated. It's an easy way to say. It doesn't matter where you plug in positive or negative, you will always get the same y. Yes? Because you see, if we put 2, we get 3. If we put -2, we also get the same 3. If we put 4 or -4, doesn't matter which one of the two is it, we'll always get 9. Why is this? What do you think the function is responsible for this behavior? The x squared. Right? And the function, when saying the function, meaning the formula. The x squared, the x is only showing up in here and it's being squared. This is telling you that this doesn't matter whether x is positive or negative. The square is still in the negative anyways. Yes? So regardless whether you plug in a positive or negative number, the output will always be the same. Okay? What matters is the absolute value of that number. What that means is that when it comes to the graph, what happens to the right side is going to mirror over to the left side as well. Okay? Because the y-axis will look like a mirror. Because whatever you get on the positive x, you're going to have the same behavior on the negative part of the x-axis. Okay? As your classmate was pointed out, this means a function is symmetric with respect to the y-axis. We have a name for these. These functions are called even functions. Okay? So in the next section, we're going to talk about symmetry, which is we're just going to touch on two types, which is even or odd functions. Okay. Anyways, good. So now what we do here is we just plot. And again, we put our points. So let's see, 0, 1. So that means that we have a point here on the graph. Then 2, 3. So this is 1, this is 2, this is 3. There's a point on the graph. Then -2, 3, -1, -2. And then when we plug in 4, we get 9. So let's say this is 3, this is 4. Okay. 4, 5, 6, 7. Ah, nice. 4, 5, 6, 7, 8, 9. Okay. Oh, so we have room for it. So that's 4, 9. And then similarly on this side, right? -3, -4. That's -4, 9. And then hopefully you agree that, as I move towards the right side here, what's going to happen? So I start throwing in values that are bigger and bigger, greater than 4. What's going to happen? What's going to happen to the y values? For example, is it ever going to come back down? No, it's just going to keep getting bigger and bigger. Does everybody see this? We're squaring that number. Okay, we're dividing by 2 and then plus 1. But when you square something, it starts shooting off very fast. Like a 5 already at 25, right? and so on. Okay, so we can see that this is going to keep going up, and then of course, because it keeps going up this way, it's going to keep going up the other way because of the symmetry behavior. Now our job is to kind of join all of these dots with a curve that is reasonable, and then the question is, should we use a straight line or shouldn't we use a straight line? Well, in this case, if you use a straight line, for example, then there is no way for you to capture this guy and let alone these points over here. Okay, so you're kind of forced to do a little curvy thing, and of course, once you study to see this shape, you either plot more points, or you wait until we know a little bit more about this function. Anyways, the understanding is that this keeps going up this way, keeps going up this way. Okay, if you want to get a more precise sketch, just have to pick a bunch of points in here so that you have more points and so on. Okay, so computers, they pick thousands, millions of points in a split of a second, and then you can precisely trace the function. Anyway, this is the general shape. Okay, now why is it like this and not a little peak here and so on? In calculus, you will understand that. Okay, because this is what we call a smooth function, so it has to be differential everywhere. So you cannot have like sharp corner, nothing like that. All right. Any questions about this picture? Okay. So then the reason why I draw this picture is to have a visualization of the problem that we have at hand. So the question is, given this function, I want you to find the slope of the line that passes through these 2 points. Now these points, we can see them on the picture. The point 0, f of 0 is this point over here. And the point 2, f of 2 is this point over here. And then the question is, there is a line here. This is called a secant line to the graph of the function. And then what we want is to find the slope of this line, right? So this is a line, y equal mx plus b. And what's the slope of this line? So in these letters, which one corresponds to the slope? Is it m or is it b? M, right? So we are after this little number. Okay, this is what we want, slope. B is the y-intercept. Okay. Okay, so how do we calculate the slope of a line? Okay, so what will be the slope in this case? What's the slope?
This is slope y2 minus y1 over x2 minus x1.
Yes, that's a formula. But you can see it very easily here. You have the picture. How do you find the slope? The slope is 1, right? So, like the person said, so changing y. So, basically the slope is a ratio, okay? And then how do you find that ratio? Just pick 2 points on the line, whatever you want, and just figure out, for example, if the line is going up, is the slope positive or negative? If the line is going up, is it positive or negative, the slope? So when the line goes up, the slope is positive. If the line goes down, it's negative. So you already know it's positive. So now you can find the slope using a ratio. Just pick 2 points and figure out how much you need to go. In this case, to jump from this bottom point to the top one, I need to go up and right. Yes? Just figure out how many steps you need to do. So I need to go up 2 units and then right 2 units. So that's 2 over 2, which is 1. Okay? That's a rise over wrong thing, people say. So just looking at the picture, you can easily see that the answer is that the slope is 1. Okay? Now, of course, we have a formula. So the slope that we call it m. So, we typically say y2 minus y1 over x2 minus x1. So this is the difference of the y's, that tells you the change in y, divided by the difference of the x's, or the change in x. Okay? This is your rise over run. Now, the rise over run is misleading because if your line is going down, it's not really rise over run. It's fall over run because you are falling to go to the other point. You're not really rising because you read stuff from left to right. But anyways, changing y over changing x is your formula for the slope, which in this particular case, what is y2? Y2 is f of 2. And what is y1? That's f of 0 over 2 minus 0. Okay? And then, of course, you can plug in, I wrote this for a reason, but now you can plug in this, so that would be 3 minus 1 over 2 minus 0. So that's your 2 over 2, which is positive 1. Okay? So this is slope of the line. This is something that you already have seen. The point is that now this has another name. This number, this one, is what we call the average rate of change. Okay? So we call this number the average rate of change of the function from 0 to 2. Okay? So if you need to compute the average rate of change of a function from one value to another one, this is the question that they are asking you. What's the slope of the corresponding line? That's what you have to do. And therefore, we have a formula for it. Okay? So let me say that. So remark, this number, n equals 1, is called the average rate of change of f from 0 to 2. Okay? So when they ask you, if you need to find the average rate of change of a function from one point to another one, all you have to do is find the slope of the line that joins those 2 points. Okay? That's all it is. And you have a formula for it. y2 minus y1 over x2 minus x1. It's just that in this case, because we have a function, instead of using y2, y1, we use f of x2 minus f of x1. Okay? Whatever your x2 and your x1. Do you understand this? So it's just a different name to the same idea that you're used to. So, definition, let y equal f of x be a function and let a and b be 2 elements in the domain with a less than b, let's say a less than b, then the average, and unfortunately we don't have a shorthand notation for this, so the average rate of change of f from A to B is important, from A to B, from the smallest to the bigger, is given by the following expression, is equal to f of B minus f of A divided by B minus A. But all this is the slope of a line that passes through the point A comma f of A, B comma f of B. Okay? So in other words, this right here, this is just the slope of the line that passes through A comma f of A and B comma f of B. Okay? And this is a secant line. In calculus, when you talk about derivatives, we're going to be interested in tangent lines. So you want to make sense of the slope of a tangent line at a given point. And to do that, the idea is we look at secant lines and then start getting the points closer and closer to each other, and we try to follow those slopes of those secant lines and see whether they get close to some value or not. Okay? So that's why we need an expression or a formula that allows you to calculate the slope of these secant lines. And that's the one that we're going to introduce soon, which is what we call the difference quotient. Because this is now one line, this is one number. We want to make this a moving picture, so we want to be able to track all possible secant lines on the graph, okay? And then be able to find all possible slopes of the secant lines, and then that's what the difference quotient is. Anyway, so we're gonna get there pretty soon. But right now, the point is that our rate of change is a very easy idea. It's just slope of a line, okay? The line passing through those 2 points. It's just that you will only be given the x's, you're not given the y's because you have the function. You can always find the y. So from A to B, those are your 2 x's. Do you understand this? Okay, so let's see, do this little example. So find the average rate of change of the function f of x equals 2x cubed plus 1 from 1 to 4. Okay, so who can tell me what's the formula in this case? What should I write? So what should we write?
So f of 4 minus f of 1
F of 4 minus f of 1
over 4 minus 1.
over 4 minus 1. Does everybody understand this? Now you just compute this. Now remember, this means go to the function and plug in 4. Not to the y. This means go to the function and plug in 1. So what's f of 4? So that's 64 times 2, 128, plus 1, 129. So that's 129 minus 3, that's f of 1, that's 3, over 4 minus 1, that's a 3. So that's 126 over 3, and we can divide this, so that's 42, right? Yes, 42. So the average rate of change of f from 1 to 4 is 42. In other words, the slope of the line that passes through the point 1, 3 and 4, 129, the slope of that line is 42. Okay? So again, if this was, for example, a physics problem, and this happens to be a function that models the position of a certain particle, then what we are saying here is, let's say, over the time measured in minutes, or let's say in seconds, then it means that over this interval of time, from 1 to 4 seconds, the average velocity or average speed was 42. Okay? Whatever units is miles per second, or well, that's that's too fast. So inches per second or something like that. I don't know. Okay, but the point is that it will have a meaning if this function had a physical meaning attached to it. Okay. All right. Questions? Do you understand this? It's very straightforward. You just have this little formula. Now, as I mentioned, so I want to talk about the difference quotient now. So difference quotient. And basically what we want is, we want to use the same idea. We want to be able to look at the slope of a certain line, but I want to be able to move this picture. In other words, if I now change this other line, I want a formula, I want an expression that keeps track of this slope, the slope of the other line, and so on and so forth. So if I keep moving, typically we want to fix a point. Let's say I fix this point, and then I just let my other point change. So given this point, you get this line. But now If I put another point over here, I'm gonna get another line. I want the slope of that line. And then if I keep moving my point around the function, I'm gonna get a bunch of secant lines. Do you understand what I'm saying? We want a formula. We want one expression that keeps track of all the slopes. Okay? At once. That's what the difference quotient is. So all I'm gonna do is I'm gonna look at a picture like this. I'm gonna change names of the average rate of change. Okay? So, but I'm gonna do it in general. So let y equal f of x be a function. Then let's say this function has some graph. I don't know, whatever it is. Just put it here. So let's say this is your function y equal f of x. Let's say this is a, and then this one over here is happens to b. So this is the point a comma f of a, and this is b comma f of b. Okay. And as you know, when you find average rate of change, what we're doing is we're finding the slope of this line. So we know the slope of this line is f of b minus f of a over b minus a. That's the average rate of change of the function from a to b. Now we want to make this a moving picture. For example, let's say that we want to fix this point. And then if I give you another point, let's say this one, you're gonna get a new line. I wanna know the slope of this line as well. If I fix another point over here, and then I wanna know the slope of this line, and so on and so forth, okay? So this is the kind of game that we wanna play. And instead of computing that slope every single time, I just want a formula that I plug in something quick, and we get the slope. The desired slope. So to achieve that, I need to make this a moving picture. So to do that, I don't want these things to be fixed numbers anymore. Okay, so I want to introduce a variable. So here is the idea. First, I'm just gonna change names. I'm gonna call this guy, I'm gonna call it X. Okay? So A, I'm gonna call it X. So this will allow me now, whatever X I give you, that will position this point wherever you want on the graph. Yes? Now, this, I want to, instead of calling this B, I want to talk about the distance between A and B. Okay? The relative distance, let's call it H. So I'm gonna call this H. So if this is H, then B will be X plus H. You understand this? Because this is X, then this distance is H, then B is just X plus H. Does that make sense? So now H tells you how close you want these 2 points to be. X is going to position one of the points somewhere in the graph, and H tells you how close you want your second point to be to the first. Do you understand the purpose of these two quantities? Yes? Now, with this new name, these are the same A and B, but now we just change names. Let's write down the formulas. So now f of A, what's the name that it receives? This is just f of x. And f of B, what's the name for this? That would be f of x plus h. So we come to our average rate of change formula, and we just write down our names. So instead of f of b, we have f of x plus h. Instead of f of a, we have f of x. And then what's b minus a? We can put the thing, or we use our intuition. So what's b minus a? That's exactly this distance, right? Which is just h. But let's put in what it is. So x plus h minus x. So we have small simplification in the bottom, and then we get f of x plus h minus f of x over h. In other words, this right here is what we call the difference quotient of a function, but this is just the average rate of change from x to x plus h. That's all it is. Okay? But now we just got a moving picture because now you have two variables here. You have x and you have h. Give me whatever x you want. That's going to position one of the points on the graph, and then h. Give me an h. That's going to give me a distance to give me my second point. And then you find. If we agree that we fix, say, this h, then just give me whatever x you want, and then we'll be able to navigate through the entire graph. Or if you fix x and then you let h change. In calculus, what you're going to do is you're going to fix this point, and then you're gonna make h very tiny, closer and closer to 0. Because you see, let's say that I fix this point. Actually, let me fix this one. It's nicer if I fix this one. What's gonna happen if I fix this one? This is my h, right? Then I'm gonna make h be closer and closer to 0. So what does that mean to make h close to 0? This a, I'm bringing it closer and closer to the b. Do you see that? So that means on the graph, that point is gonna be moving like this. The smaller h is, we get this sequence of points on the graph. We understand this? Now, this function, what's the job of this function? This function is computing all the slopes that we get of what lines? This one, and this one, and so on. Let me just draw. I'm just gonna draw the last one so you see, hopefully. This secant line over here. But the point is that the closer and closer our point gets towards our point of interest, which in this case would be b comma f of b for some reason, then all of these secant lines that we know how to find the slope, hopefully you agree that they get closer and closer to a special line, which would be a line that only touches the graph of the function at this point, which is what we call the tangent line. Okay? So this is one of the main ideas in calculus, to make sense of this. And this is actually how you do it. Okay? So you start with 2 points, far away, and then you say, okay, let me make this point closer and closer to my point of interest, and I'm gonna watch out what happens to all the slopes. And if they get close to something, then that number that they're getting close to, we call it the slope of the tangent line, which another fancy name is the derivative of the function over there at this point. And what expression allows you to keep track of all of these different slopes? This one over here, the difference quotient. Okay? And because you want h to be very small, then what you want to do is take this expression and consider the limit as h approaches 0. Limit is what this approaches to, is this expression getting close to something when h is very small, when h approaches 0. Okay? So you're going to be doing that in calculus if you need to take calculus. So that's the reason why we're spending time here in this concept. Okay? I mean, we're not going to use it too much other than being able to compute it, but you need to know its meaning because you're going to need it later on if you have to go a little bit further. Okay, anyways, but the point is that this is just our rate of change. Okay, we just change names. Instead of 2 points, now we have variables. Okay, so this is what we call difference quotient. So definition. The difference quotient of a function f is the following expression. Is expression f of x plus h minus f of x over h. Okay, and remember that this is just the average rate of change of f from x to x plus h, which again, that's just the slope of the line through the points x comma f of x and x plus h comma f of x plus h. Okay, that's all it is. And your job is to be able to simplify this as much as you can, given a function. Do you have any questions on this? For example, let me just show you quickly. I'm teaching a Cal 1 this semester, and when we talk about derivatives, let's see, where is it? Definition should be somewhere in here. You see, that's exactly the idea that we do. So this thing that I'm explaining to you is exactly what we're doing in calculus. You start with the notion of a secant line, and then you want to make sense of a tangent line, the blue line over here. So the idea is to make this point go towards P, and then keep track of all the slopes. Okay? And to do that, it's just difference quotient. Okay? That's what you do, and then you take the limit because you want the points to be close to each other. Then you want that h to be very small, so we take the limit that h approaches 0. Okay? But right now, when you're doing problems here, I'll show you the examples. This is the kind of thing that we're going to do now. But I want you to see ahead because you need to understand what it means to simplify a difference quotient. So, for example, let's look at something simpler. So that's fine, this one. So if you have a function like this, to find the derivative means to take the limit of the difference quotient, okay? We are not doing the limit. Right now, we're just interested in this part, the difference quotient part, okay? But the thing is that basically taking a limit, most of the time is just plugging in whatever the variable is approaching to, unless you run into an issue. Here, if you make h equals 0, what's going to happen is, as you can see, you're going to get f of x minus f of x, that's 0 on top, and you have 0 in the bottom, so 0 over 0. That's an indeterminate form. So before you actually plug in, what you need to do is you need to do algebra, which is what we are learning now. And the algebra here means simplify this expression, and your job is to make sure that this h is gone. Why? Because this h is the one responsible for the 0 in the denominator. A 0 in the top is not a problem, because 0 divided by something is just 0. The only issue is when you do 0 over 0, because you cannot divide by 0. Okay? That's an indeterminate form. So, to simplify a difference quotient means to make sure that this h, the one down here, is gone. So you do whatever it takes until that happens. And in this case, you see, after this step, we might simplify this h in the bottom, and then we get something, we plug in, whatever has an h is gone, and then that's why we get the x squared plus 2. Okay? You'll be doing that in calculus, but our job now is this in between part, these steps. Okay? So the difference quotient of this function will be this expression over here, the one in parentheses. For example, we're going to do these ones also. Here is another function, 1 over x. Again, the same idea. Our job is to cancel this h. And that happened in this step. So the answer will be negative 1 over x times x plus h. That will be the difference quotient. Okay? So let's do this kind of things now. All right, so those are calculations that are needed. So, you have to have the skill to be able to do this. And we kind of practiced this last time when we talk about function notation. We practiced, for example, evaluating this type of expression. Now, we didn't do the over h, but we did do the top part. Okay? So now let's do the entire package. So let's see, examples, find the difference quotient. Find the difference quotient, and then let's do 2x squared minus x plus 1. This is, in general, this is a little bit tedious many times, and also sometimes it's very difficult, to not say almost impossible. I mean, it could be very difficult. That's why you spend a lot of time in calculus learning a bunch of rules and techniques to be able to find the useful functions without having to use the difference quotient approach. Because when the function is like this, yes, it's easy, but if I start throwing in a bunch of square roots and weird things going on in my formula, then it becomes a nightmare. So, but anyways, this is the root of one of the main ideas in calculus. Okay, so here we have 5 functions. Let's go ahead and let's find the difference quotient of this. Okay, so let's see. Let's first do a sanity check. Let's do number 2. By sanity check, I mean let's make sure that the formula is giving what it's supposed to give. Let's see, for number 2, what do you think we should get as an answer? Without you compute anything. If you understand the meaning, you should be able to tell me the answer. What should we get as an answer for number 2? So don't compute anything. Just look at it and tell me. What should we get for number 2? Just think about what's the difference quotient. What does the difference quotient do?
Would you just grab a number because it's just a slope?
The slope of what? Okay, but what answer would you get in this case? Let's see, what's the difference quotient supposed to be doing? It's supposed to track all possible slopes of secant lines on the graph, yes? Now, if our graph happens to be a line itself, the secant line means pick 2 points and draw the line joining the 2 points, right? But if your graph is already a line, if you pick 2 points and you draw the line past those 2 points, what line is that? That's the one that we had to begin with, right? So no matter what 2 points you pick, you will always get the same slope because it's the same line. What line? The one that we have. What's the slope? 2. So we better get 2 as an answer for problem number 2. So that's why I call it a sanity check, because we already know what to expect. We know what the answer. Let's use the formula and let's make sure that we do get 2. Do you understand what I'm saying? You know, maybe I'm lying to you here. You know, at this point, this formula doesn't work. So let's at least get something that we know what the answer should be. Let's use it now with the formula and see that they match. Okay? But you know, we expect the answer to be 2 because that's the only possible slope that we can have for this graph. Okay? So let's do that. That one first. So let's do number 2 first. Okay, so difference quotient, that's f of x plus h minus f of x over h. So let's evaluate. What does this mean? F of x plus h, how do we do this? What is this telling you? That means go to the function, every place that you see an x, write x plus h. Okay? So that's 2. So remember, use parentheses. Okay? Instead of x, I put a parenthesis, and then inside the parenthesis, I plug in what we have. Then minus f of x, that's the entire function. Now be careful, because f is a binomial, that minus is going to affect the term, so you have to put in parentheses. All over h. And now, you know, simplify. So let's see what do we get here. So we have 2x plus 2h minus 3 minus 2x plus 3 over h. So the 3's cancel, the 2x cancel. So we end up with 2h over h. And remember, to simplify difference quotient means our job is to get rid of this h down here. So you don't stop until you manage to simplify that h. Okay? Until you have done that, this is not considered simplified. And in this case, it nicely happens. So we do get, the answer is 2, as expected. So in other words, if your function is already a line, the difference quotient is just the slope of the line. Okay? So of course, what's interesting is, what if your function is not a line? Then we are going to obtain a function, which will depend on both x and h. It's a 2-variable function, really. Okay? Questions on this one? Right? So do number 1. So we do number 1, and then I'll let you do number 3. Now this one is slightly tedious, but you know, that's life. Not everything is nice. Okay. So f of x plus h minus f of x over h. Now we go and we plug in, so just be careful, okay? So strongly encourage you to go and put parentheses everywhere that you see an x, then fill in inside the parentheses the input. So that's the f of x plus h part. Then minus f of x, which is 2x squared minus x plus 1. All of these divided by h. Yes? Remember, our job is to get rid of this guy down here. So we don't stop until we accomplish this. Okay, so now it's just expanding and doing whatever we can here. So let's see. That would be x squared plus 2xh plus h squared, then minus x minus h plus 1 minus 2x squared plus x minus 1 over h. Again, I'm gonna get rid of this guy. Let's see, I already see some cancellations here. The x's are gone, these ones are gone. Let's keep going. So distribute the 2, it's 2x squared plus 4xh plus 2h squared. Then we have minus h minus 2x squared all over h. This is our target down here, so we're not done. So we see, let's see, the 2x squares, they cancel each other, and then that's it. We don't have anything else that cancel. But now, luckily enough, we see that whatever remains at the top, everything has an h, right? So we can factor out h, which will then cancel this one over here. This is good news. So we can take on h, so we get 4x plus 2h minus 1 over h, and finally cancellation happens, so we get 4x plus 2h minus 1. So the difference quotient for this function is this one, okay? So once again, this is a formula, and what this formula is doing for us is, if you give me an x and an h, it's going to give you the slope of the corresponding signal line, okay? All right, questions? Yes?
Does it necessarily matter the order we put it in? Because I put it as 2h plus 4x minus 1. Is that
2h plus 4x?
minus 1? Does
Yeah.
it matter the order we put it in?
I mean, 2 plus 3 is the same thing as 3 plus 2.
Yeah.
All right. You okay with this? Very good. So, for example, what would be the derivative of this function in this case? So, if you use the definition, you will be doing this, but then there will be one extra step. What will be the last step? You want the 2 points to be close to each other, so you take the limit as h approaches 0. That means plug in 0. We cannot plug in 0 up here, but you can plug in 0 down here. What happens if you plug in 0? What do you get?
4x minus 1.
You get 4x minus 1. That will be the derivative of this function. Okay? Now, of course, you don't want to be doing this every single time that you get something like this, so you develop some certain techniques to compute this 4x minus 1 way quicker. Okay? But really, this is what's happening. Okay? All right. Any questions? Okay, so try number 3. All right, do you have an answer for this? Okay, so what do you get? Let's see, f of x plus h minus f of x over h. What answer do you get?
H plus 2x plus 1.
H plus 2x plus 1. Okay. Everybody getting this? There's a problem here. There's something wrong. Yes?
I got 2x plus h minus 2.
Okay. 2x plus h minus 2. That looks a little bit more reasonable. Anybody else?
I got 2x plus h minus 1.
Okay, 2x plus h minus 1. Okay. Again, this minus 1, I'm curious where this minus 1 is coming from. So you have to be careful. But we'll see. We'll figure it out. All right, let's see. Let's do it. Okay, so again, this means, remember, go to the formula, and wherever you see an x, put x plus h. So I'm going to put parentheses first, and then put my x plus h inside. Then minus the function itself. So remember, use parentheses here because that minus is going to affect the entire expression. Okay? All over h. Is everybody okay up to here? Okay, so let's clean this up. So that would be x squared plus 2xh plus h squared, then minus 2x minus 2h, then minus x squared plus 2x, all over h. Everybody okay? All right, so let's see. Now the cancellation party begins. This guy cancel with this one cancel with this one. Okay, party is over. There's no more. Actually, there are a bunch of two, so there is no one left over. So maybe when you distribute it here, I don't know, something happened between the negative. Anyways, after you cancel, then you know the terms that remain on top, they all have an h. We have 3 terms on top, each of them with an h, so we can factor that h out. So factor the h, so we get 2x plus h minus 2 over h. Now we finally get to cancel the h that we wanted, and then we end up with 2x plus h minus 2. Okay? All right. So did you find what the problem was? Okay, good. Any questions? Okay. So now, you know, typically when it's a polynomial function, this is what happens. You expand, you need to, unfortunately, you need to expand the parentheses. So if it would have been to the 10th power, then, you know, it would be really a pain here. But it's what it is. You do it. And then, you know, eventually everything will cancel out, and then whatever remains will have a bunch of h. You will be able to factor out an h that will ultimately cancel the guy. Okay? And now what if you have now an expression that contains fractions or radicals? So just to give you a taste of how that works, let me just, you know, because the technique is different. Because here the idea is plug in, expand the parentheses, simplify, and then everything will work out nice. But when you have other type of expression, you need to use a different technique. Like for example, if you have a fraction, I'm just going to do the simplest one, okay? 1 over x. So we want to find the difference quotient here. Let's see, when we plug in, remember here you have to be very careful, make sure you understand how to plug in. So that's 1 over x plus h, that's the f of x plus h part, minus 1 over x, that's the f of x part, over h. Okay? Now here there's no parentheses, nothing like that to simplify, but what we have is little fractions. That's what we call a complex fraction. So the idea here is that we clean up all denominators, okay? So we multiply top and bottom by the LCD to make this a single fraction. In this case, we talked about finding LCD at the beginning. The LCD is x times x plus h. That's the least common denominator. So I'm going to multiply top and bottom by x times x plus h. All right, so when we do that, in the top, the first term, the x plus h cancel, and we get x. Then minus the second term, the x cancel, and we get x plus h. And then in the bottom is just what it is. So now just leave it like that. And the reason why you should not distribute is because remember, our target is this h. We want to cancel this h, so you want to leave it as a factor. You want to leave it multiplying with the hope that there will be an h on top that we can then cancel out. Okay? If you distribute this, then you're not going to be able to simplify this h. So you leave it like that in product form. Do you understand this up to this step? Again, there are 2 little fractions here. We just want to get rid of this fraction. So we multiply by the LCD. The LCD is x times x plus h, the product of these two. So I multiply top and bottom by that quantity. That means every single term gets multiplied by x times x plus h. When you do the first product, the x plus h cancel and you're left with x times 1. That's why there's an x here. Minus, when you do the second product, the x cancel and then you are left with x plus h times 1. So that's why you have that here. And here in the bottom, there's nothing to cancel, so it's just h times this guy. Okay? So we did. Now there are no little fractions anymore. We just have one fraction. let's continue here. So it's kind of clear what to do. We simplify the parentheses on top by distributing the negative. And then we see that the x cancel out. So we end up with negative h over hx times x plus h. And then we manage to cancel the h that we wanted. So we end up with negative 1 on top, then x times x plus h. And we're done because, we managed, remember, we wanted to cancel this h. And this one. So we did it, so we're done. And there's really nothing more to do here. Okay, questions? For example, what's the derivative of 1 over x? I mean, I already told you. What do you do to find the derivative? You do this process and then you plug in h equals 0. So now that you have this, what happens if you plug in h equals 0? You get negative 1 over x squared. That's the derivative of 1 over x. Okay? But hey, you don't have to worry about that. But you need to worry about this. Okay? But this is really the hard part. After that, it's just plugging in. All right. Are you okay? And then, that's a technique. If a function is a rational function or has a fraction, you will end up having some sort of denominator. So the idea here is that you will need to create denominators before you move on. Okay? So if it's polynomials, you have a bunch of parentheses that you need to expand. If you have a fraction, you need to create denominators. What if you have a radical? And again, just gonna do the simplest case. It's something like this. So what do you do if you have square root of x, for example? So this would be square root of x plus h minus square root of x over h. So you have to be careful, make sure that you understand how to evaluate this. This means go to the function where you see an x, you put x plus h. So x plus h is inside the square root. Okay? It's not outside the plus h. Do you understand this? So you get this minus the function, which is square root of x over h. All right. Now, once again, there are no parentheses here to simplify, nothing like that. And our job is to get rid of this guy down here. That's the h that we want to simplify somehow. So we need to do whatever it takes to make that happen. So what can we do? Yes?
You could times multiply h on both sides to get rid of h. Oh,
No. Okay, so remember, this is one quantity. This is not an equation. This is one quantity, and then we're just writing equivalent space. So you're moving this way all the time. In other words, there's no moving around.
Yeah.
Okay. So what can we do to get rid of that h down there? For example, let's do some wishful thinking. What's in the way of us being able to get rid of that h? What would be nice to have in here to be able to get rid of that h? Yes?
An h in the numerator.
Say that again?
H in the numerator.
Okay, an h in the numerator. How could we get an h on the numerator? Yes?
We gotta have over the radical.
Okay, how would you do that?
Good question.
So you see, the radical is in the way. If we didn't have the square roots here, what could we do? Imagine that without the square root. So take the square root out of it.
The x's will cancel out.
We could cancel out the x's, and we will have the h that we need on top to cancel with the bottom, right? So let's think about how can we make that happen? How can we get rid of the square roots in the top? Yes?
Do we times it by the conjugate?
Very good. So here, if you want to get rid of the square roots in the top, what you can do is multiply by the conjugate, top and bottom. Because if you multiply top and, remember, not just top, you need to do top and bottom, right? Because we don't want to change the expression, so we need to get something equivalent. So if we multiply top and bottom by the conjugate, on top, we're going to have a difference of squares. This guy squared minus this guy squared. And what the square is going to do is going to remove the square root for us. Do you understand what I'm saying? And we will have what we want. No square roots, and then we can cancel the x's and get an h that will ultimately get rid of this one down here. Do you understand this? So, the technique is a little bit different than the ones before. So here, the idea is that we multiply top and bottom by the conjugate of the top. You okay with this? All right. So let's see, if we do that, what do we get on top? Remember, multiplying by the conjugate, that's a minus b times a plus b. So the product is a squared minus b squared. So let's see, write down the steps. So this guy squared minus this guy squared over, and then, the product is what it is. Now, leave it as a product. Don't distribute the h, because our job is to cancel this guy, so you don't want to distribute it. You want to leave it like that as a factor, so we could simplify when the opportunity arises. Okay, so now the magic happens. Square roots are gone. Then we simplify the x's, so we end up with h over h times square root of x plus h plus square root of x. Now we can finally cancel the h as well. And we managed to cancel the h that we wanted, so we're done. All right, questions? Are you okay with this? So again, depending on the thing is that depending on the function is what you do. Okay, this is what happens. So this could get pretty complicated really try quickly when I start changing this formula here. Okay, so that's why you spend some time learning techniques to find derivative in fact, to avoid doing this every single time. That's the point. Okay, but that's the root of everything. Okay, questions? Okay, good.